So today in section 9.1, we're basically going to take everything that we learned about correlation and regression back in chapter 2, and then we're going to take everything we know about doing statistical inference, and we're going to kind of mash them up together. So we're going to do inference for slope and correlation. So first, we're going to just review a little bit some of the stuff that we learned back in chapter 2. And you might remember we already looked at this example back in chapter 2. We wanted to know if you could estimate the temperature on a summer evening just by listening to crickets chirp. And so to do that, we were going to examine this relationship between two quantitative variables. And what's the very first thing that we always do with our set of data? Graph it, exactly. And so the type of graph, what's the type of graph that we use to look at two quantitative variables? Perfect, scatter plot. Okay, so we're going to do a graph, and the graph we're going to use is a scatter plot. And remember, on a scatter plot, we're looking for three basic things. So what are the three things that we're looking for on our scatter plot? Perfect, form, direction, and strength. So this one is the chirps and the temperature. So looking at this, what kind of form would you say it has? And remember, our options for form were basically linear and not linear. Okay, and this is where we talked about doing the fat hot dog test. If we could kind of look at the overall pattern of the points, and they tended to look like a fat hot dog. This one actually looks like kind of a skinny hot dog. Then it was going to be linear. Okay, and if it looked a little bit more rainbow or smiley face or banana, then we were going to say that it was not linear. And then direction, we can have either positive or negative. So it's positive if as x increases, y also increases, and then it's negative if as x increases, y decreases. And then the last thing that we looked at was the strength. And for strength, we're looking at weak, moderate, strong. Those are the basic ones. You can kind of combine them, say like moderately strong or moderately weak, or just add an ish on the end. I like to do that too, moderate-ish. And this one looks pretty strong here. By strength, we mean how closely do the points fit the form? And specifically on these linear relationships, like how close do they get to the line? So in this case, like I said, form, we said it was linear, direction, positive, and strength was, this one was really strong because look how close they are to that line, like they're practically sitting on it. All right, so once we graph the data, the second step is to look at numerical summaries, or sometimes we call those descriptive statistics. So who remembers the name of the numerical summary that describes the strength of the linear relationship between x and y? So there's a quantity we talked about that measures how strong the linear relationship between x and y is. Yeah, correlation. Okay, so correlation, and here in StatKey, remember if we look at two quantitative variables, it gives us all this information on the side, and it will tell us the correlation. So for the chirps and the temperature, we see that it has a correlation of 0.991. And 0.991 would be like a really, really, really strong linear relationship. So thinking about correlation, what are some other things that you remember about correlation? Like what are some other characteristics of correlation? So first of all, maybe what kind of values can correlation take? Okay, so correlation has to be a number between -1 and +1. Okay, the closer you are to -1 or +1, the stronger the relationship, and the closer you are to 0, the weaker the relationship. So remember, the sign on correlation just indicates the direction. And if I look at the absolute value, then the closer it is to 1, then the stronger it is. So the sign does not indicate strength, it only indicates direction. When we're looking at correlation, what type of variables can I compute correlation with? Both variables have to be the same type, and what is that type? I can only compute correlation for two 2 quantitative variables, right? So correlation can only be computed for 2 quantitative variables. And thinking about correlation, would you say that correlation is resistant or not resistant? Yeah, correlation is definitely not resistant. So remember, resistant means that it's not as affected by outliers. So if it's not resistant, that means that it is affected by outliers. And correlation, if you remember back from chapter 2, is like highly affected by outliers. And that's why we said we have to watch out for outliers, and especially those influential observation outliers that can affect correlation and also our regression line. Okay, so now we're ready to move on to step 3. So first step was graph it. Second step is numerical summaries. Step 3 is model the relationship. And the type of model that we use is called the least squares regression line. And it has that kind of basic slope intercept type form. So again, here in StatKey, we can get the slope and intercept to come up with the equation for our least squares regression line. So here we have predicted value for temperature is equal to 37.7 plus 0.23 times chirps. So this 37.7, what do we call this one? This one is our intercept, because it says it right there. Okay, so this one's our intercept value. And the way that we kind of interpret that is that it's the value for temperature when x is equal to 0. So in this scenario here, it's basically saying when the crickets stop chirping, so there's 0 chirps per minute, then the temperature outside is 37.7 degrees. And in general, the intercept is not our favorite part of the model, because only sometimes is it even going to make sense in the context of the problem. But it's important to have the intercept because it makes our model work and everything else. So we keep it around, but it's not our favorite part. Our favorite part of the model is the slope. And we love the slope because it really quantifies the relationship between x and y. So it gives so much more information about that relationship. And remember, and we've kind of kept up on this a little bit, I think, interpreting slope, but make sure you remember how to interpret slope if you've forgotten. So if my slope is 0.23, then I would say for every 1 additional chirp per minute in the chirp rate, then temperature increases by 0.23 degrees. So you might want to even put that kind of our little pattern for interpreting slope, put that somewhere on your 1 page of notes for the exam. All right, and once we have our model, then we can use it for all kinds of things. One thing that we like to do with our model is make predictions. And if we're given the model, as long as somebody gives us an X value, then we can just plug that in and use that to make the prediction. So for example, if you listen, you hear crickets chirping about 140 times per minute, then what would be the predicted value or your best guess at the outside temperature? So go ahead and do that calculation, and you can throw your answer in the chat window when you have it done. Perfect. So we're going to take that 140 here. We're going to plug it right in here for the chirps, and then we're just going to solve. So if I plug in 140, then I get a predicted temperature of 69.9. So the model that we used in chapter 2, like kind of the basic model, was this. We had y hat equals a plus bx. And in chapter 9, we're going to use this same basic format for this model, but we're going to change how we label our terms. So in this chapter, we're going to change all of our notation. So instead of a and b for the intercept and slope, we're going to use b0 and b1 for the intercept and slope. And this new notation, it makes sense with what's going on in the end part of the book here. In chapter 9, we're doing something called simple linear regression. And you notice that we have that word a lot here, simple linear model. simple. And that doesn't mean that it's easy. So if you're like, wow, she keeps calling it simple, but I don't think it's simple. Simple means that we just have one X and one Y. And if we had time in our class, then we would go into chapter 10. And in chapter 10, we do multiple regression. And in multiple regression, then you have lots of X's and one Y. And so using this notation down here makes it a lot easier to kind of expand our model to include more X values, because we could say B1 X1 plus B2 X2, you know, et cetera, for however many X's that we wanted to add. So I understand why the authors of your textbook want to use this model, which is what we're changing to. But I am a little bothered that they made us learn this notation in chapter 2. I feel like, hey, if they wanted us to get to this eventually, like, you know, we're big boys and girls, we could have handled it back in chapter 2 so that we didn't have to change horses midstream here in chapter 9. So if this is going to be a little bit confusing to you, you might want to just write this somewhere and just kind of be like, okay, A, the intercept, we now call it B naught, okay, and B, the slope, now we're going to call it B1 from now on. And another thing that we're going to start doing here in chapter 9 is in chapter 2, we were using sample data to come up with our regression model. So our A and our B, and now we're calling them B naught and B1, were based on sample data. And if I was to take a new sample and compute the slope and intercept from the new sample, would you expect that we would get the exact same numbers as we did with the first sample? Well, no, of course not, right? So, and if I took a third sample, I'd get even different numbers. Because as it turns out, then this B naught and this B1 are actually sample statistics the same way that X bar is a sample statistic and P hat is a sample statistic and R is a sample statistic, S is a sample statistic. And sample statistics vary from sample to sample. And the sample statistic can be used to estimate the population parameter. So here we're going to introduce this population model, and it looks like this. So the population model would be if somehow we were able to measure everybody in the population and then make our regression model based on everybody, then this is what it would look like. It would look like Y is equal to beta naught plus beta 1 X plus epsilon. And the epsilon is basically just a term for random error. So in this model for our population, okay, because it would be based on everybody in the population, then beta naught and beta 1 are parameters. Okay, they're the unknown parameters that we're actually trying to estimate when we come up with a regression model from our sample data. So B naught and B1 are sample statistics that we're going to use to estimate beta naught and beta 1. So it's basically the same idea that we've been looking at here all along. So when our parameter was mu, then we were using X bar to estimate mu, and we used P hat to estimate P, and we've used S to estimate sigma, and R to estimate rho, and now we're going to use B naught to estimate beta naught, and B1 to estimate beta 1. So we just have these, we're realizing that when we construct that regression model based on our sample data, it's really an estimate of what the real regression line would look like if we could measure everybody in the population. And you notice that when we come up with symbols for parameters and statistics, most of the time we like to use Greek letters. So that might help you remember which one is the parameter and which one is the statistic, because beta and B sound and look a lot alike, so that can be a little bit confusing. But beta is a Greek letter, so that's going to be our parameter. Just like mu is a Greek letter, sigma, rho, those are all Greek letters. The only one that we haven't really used a Greek letter for is P. And actually some statistics textbooks do use a Greek letter for that one. All right, so if we think about the kinds of inference that we have been doing all along, when we want to do inference about mu, then there's two different methods for statistical inference that we've been talking about. And we've been doing these for the last several weeks in here. So we learned one of those methods in chapter 3. We learned another one of those methods in chapter 4, and then we've just done different variations on those same two things over and over and over again. So who remembers what either of those two statistical inference methods are? So one of them, its purpose is to estimate the value of a parameter. The other one, its purpose is to assess the evidence for a claim about the population. Anybody remember those two things? We've done them like over and over and over again. There's basically like the only things we've done. Yes, exactly. Confidence intervals and hypothesis tests. So those are the two statistical inference techniques that we've been talking about. And we've done those when we're talking about means, proportions, all kinds of stuff. So now we're going to do those same things, only we're going to apply it to regression. So we're going to look at doing a confidence interval for the slope and also a hypothesis test for the slope. And you can do it for the intercept also, but we don't really care about the intercept. Remember, it's like the unwanted stepchild. So we're just going to kind of ignore the intercept, keep it in our model because it makes it work. But the one we really are interested in that we're going to do all the inference about is going to be the slope. And really, we're doing inference about the population slope. So I don't know why I was pointing over there. Okay, so first we're going to talk about doing a confidence interval for the slope. Remember, slope is that rate of change. It tells us for every 1 unit increase in x, we can expect y to change by whatever the slope is. So now we want to do a confidence interval to see, okay, what are the plausible values for that rate of change, for that slope? And our confidence interval formula is going to look like this. So we're going to have B1, which is our sample slope, plus and minus a t star value times the standard error for the slope. So the B1 and the standard error are going to come from computer output. So we're not even going to have StatKey find these for the most part. You're going to just be given some computer output and you have to be able to figure out how do you identify what B1 and the standard error are. And if you can find those on the output, then you can see that this computation itself is going to be pretty basic. It's going to be pretty easy. And the t star value that we're going to use here is going to be based on n-2 degrees of freedom. So you might be thinking, hey, in the past, we've always used n-1. Why are we all of a sudden using n-2 degrees of freedom? And the reason for that is that when we're doing regression, we're estimating more things. So we have to estimate the intercept, and we have to estimate the slope, and we have to estimate the error. So we're estimating more. So because we have to estimate so many additional things, then that gives us fewer degrees of freedom. So that's why we have n-2. All right, so here's an example of some computer output that you might see, and we'll talk about how to figure out what B1 and the standard error are. And this is called a coefficients table. So you might see in another type of computer output, you might see something labeling it coefficients up there. But basically a coefficient table is going to have the first row, which relates to the intercept. In this case, it's calling it a constant because there's no explanatory variables attached to it. It's just a number. And then the second row here is going to be the one that you want to grab all your values from in order to do your confidence intervals and hypothesis tests. Okay, so in any of these coefficients tables, the numbers that you want are going to be on the second line. And the first line always goes with the intercept, so it can pretty much be ignored. The one exception to that is if you're trying to build your regression model and you need the value of the intercept, that's what this value right here in the coef column would be. So that would be the intercept value. All right, and then this second number on the second row here, this is my B1. So in other words, that's the slope. And then in this program, it's called SECoef. Okay, the SECoef from the second line is the only one you'll ever need, and this is the standard error that you want to use. So you will really never ever use this SE from the first line. You're always going to use the SE from the second line. All right, so looking at this, we need to come up with a 95% confidence interval for the slope. So first of all, we need to figure out our T star to plug in here. And the T star is based on degrees of freedom that are equal to n minus 2. And if we look back at our CHIRP data, there wasn't very many data points. There's only 7. So degrees of freedom would be 7 minus 5. No, why do I say that? I get all confused because I'm talking about, because I just saw the word number 5 there. Okay, degrees of freedom are equal to n minus 2, which in this case is going to be equal to 7 minus 2, which is equal to 5. So we have 5 degrees of freedom. So we're basically going to just find this the same way that we've been finding T star all along. Meaning I'm going to open up stat key here, and to find T star, I would come to where it says theoretical distributions, and I would choose this T here. I put in my degrees of freedom, which in this case was only 5. And then I'm going to click on two tail and make sure that center box has my confidence level in it. And I was just doing a 95% confidence interval this time, which is the default number that comes up here. So my T star then is this number down here at the bottom. So again, like I said, this is the same way we've been finding T star for several weeks now. So 2.571 becomes my T star value. So this 0.231, that was my slope value that I got over here. Then plus and minus my T star times my standard error. And the standard error I just got right there from that computer output. So if I multiply those together, that gives me a margin of error of 0.037. Then I take that 0.231 and I add and subtract the 0.037, which gives me a confidence interval that goes from 0.194 to 0.268. So I would say we're 95% confident or 95% sure that the slope of the model to predict temperature from cricket chirp rate is between 0.194 and 0.268 degrees. Well, degrees per chirp. So it's the slope value. All right, so that's how we're going to do confidence intervals on the slope. Like I said, it's really just a matter of identifying those 3 key things, the B1, the standard error, and then finding the correct T star. So now let's talk about doing a hypothesis test for the slope. Before we do that though, let's take a look at some different computer packages and what the output might look like coming from some different packages. So this top one, this is the one similar to one we were just looking at. This is from a program called Minitab, and you can see what it looks like here. So again, the things that we're really going to want are going to be in this second row here. You're never going to need the SE in the first row. And the only thing that the top number here in the COIF column is good for is if you're actually using it to write down your model. And you can see that this other one's from Fathom, this bottom one is from R. These are all different statistical software packages, and they basically give you all the same things. You just have to know the right place to look. And sometimes they call them slightly different things. So this one says COIF and SE COIF. This one says COIF and standard error. This one says estimate and standard error, okay, but it's all the same stuff. So as long as you know approximately where to look, you should be able to find it on everything. And it's always going to be the second line that you're looking at to get your B1 and your standard error. So yeah, there's all your slope estimates, and here's all the standard error estimates for the slope. Okay, so let's talk about doing a hypothesis test for slope. So it's going to be a hypothesis test for beta 1, okay, because beta 1 is the population slope. And when we're doing a test on slope, what we're kind of trying to say is is the x variable useful for predicting the y variable? And whether or not it's useful essentially depends on whether the slope of the line is 0 or something else. So when we write the hypotheses, the null hypothesis for a test on slope is always beta 1 equal to 0, okay? Because beta 1 equal to 0 would mean that x is not useful for predicting y. If you looked at a scatter plot, it would look like just a random scattering of points all over. It would look like a big old blob because there's no good way to draw a line through there. The best line would be a flat old line going through there. So that's my null hypothesis. And then the alternative hypothesis, we can use beta not equal to 0, or you could also use greater than or less than, depending on your scenario. Like if you already feel like your variables should have a positive relationship, then you could use greater than. Or if before you collect any data, you think, oh, these probably have a negative relationship, you could use a less than there. So a slope equaling to 0 basically means no linear relationship between the two variables. And then a slope that's different from 0 would mean that there is some kind of relationship, some kind of linear relationship between the two variables. So this is how we're going to write our hypotheses. A couple of notes about the hypotheses. Okay, first of all, the hypotheses, and you might want to write these down and kind of put a star by them or something. The hypotheses are always about the parameters, and the parameter for slope is beta 1. It's not the B1, and that can be super confusing because beta, B, they all sound really close to the same thing. So make sure you're using Greek letters in your hypotheses. Okay, so it's always about the parameter, not the statistic. The other thing is I have two betas here. I have a beta naught and I have a beta 1. And the one that I want to use to write my hypothesis about is the beta 1. So when I write my hypothesis, I need to make sure I have that subscript in there. So if you write your hypotheses like this and you just say beta equals 0 versus the alternative that beta not equal to 0, then I'm going to look at that and say, I have no idea if they thought they were doing a test on the intercept or the slope. So I'm going to have to mark that wrong. Okay, so the subscript is important because it tells me that you knew you were doing a test on the slope and not on the intercept. So those two things, make sure you're using beta and make sure it's beta 1 and keep that subscript on there when you're writing the hypotheses. So for our test statistic, we're going to follow our same basic pattern of our sample statistic minus our null value divided by the standard error. So our sample statistic is B1, and under the null hypothesis, we have 0 for a value, so it'd be B1 minus 0 divided by standard error. So really what this amounts to is B1 divided by standard error. And just as before, that B1 and that standard error, again, they're going to come from computer output. So we just have to identify those, take one, divide it by the other, bam, we have our test statistic. And that test statistic is going to have n minus 2 degrees of freedom, and we'll use StatKey to help us figure out the p-value using the t-distribution with n minus 2 degrees of freedom. All right, so let's look at this example here. So for the crickets and the chirp rate, okay, B1 here, which we can get from our little table down here from the second line, because we always use the second line. Then we're going to have 0.23067 divided by the standard error, which is the second column here, so 0.01423. And I end up with 16.21. So my test statistic, this is my test statistic, is 16.21. All right, we already mentioned that we had degrees of freedom equal to n minus 2, which should be 7 minus 2, which is 5. So if I want to find the p-value, then I would come back over here to my StatKey. I choose the t-distribution. I enter in my 5 degrees of freedom. Then In this case, we were doing a not equals to test, so that's two-tailed. And I would put in my test statistic down here, which is 16.21. And then I would multiply this floating box by 2, or add those two outside floating boxes together, which you can see even when you add them together, you basically get 0, something very, very close to 0, 0.0000, and then it would be 162 if you doubled it. So our p-value is essentially 0, which means that we have really strong evidence that the slope is different from 0, and that temperature is related to the cricket chirp rates. All right, so that's how we're going to do a hypothesis test for our slope. Now, how many of you, anybody go Black Friday shopping? I feel like this year it was like a little weird because of COVID and everything, like it wasn't the same. Like you couldn't really, I mean, back in the day, like several years ago, like I used to love Black Friday shopping because you could, line up outside the doors at like 5 a.m. And then as soon as they open the doors, you like run in and you're elbowing people out of the way and like diving across to grab like the one last Game Boy that's sitting there. But yeah, I think over the years it's well, first of all, they have started doing them on Thanksgiving Day, which I think kind of is not, it's not fun if you're not sitting out there in the cold waiting for the store to open. Like if you have to get up from Thanksgiving dinner to go to the sale, forget it. And now with COVID, it's like everybody's starting all these things. Oh, this is our Black Friday sale. Oh no, this is our Black Friday sale, because they don't want all the big crowds in there. So, COVID's killed a lot of things, including Black Friday, I feel like. But if you've liked Black Friday in the past, how many of you like getting a good deal? Maybe I should ask that question. Who likes getting a good deal? I mean, who doesn't like getting a good deal, right? I mean, that's like the best. It's like a little free high when you get like this awesome deal on something. So today I have a good deal for you. All right, so I'm going to give you a 3-for-1 special, kind of like those infomercials that you see playing in the middle of the night. Okay, if you act right now, then I'm going to give you 3 things for the price of 1. And we're going to see what those 3 things are. Okay, so just you have to think about that. Think about how excited you are about the great deal while we talk about this test for correlation. So another way that we measure the strength of association between 2 quantitative variables is to look at correlation. So we've talked about correlation in the past. R is our correlation from a sample. Rho is the correlation from a population. So it would make sense that maybe we would want to do a hypothesis test for correlation. And so we might do null hypothesis, rho equals 0 versus the alternative hypothesis, rho not equal to 0. Or again, you could do greater than or less than here as well for correlation. And there is this funky formula here that you can use to do this test for correlation. So don't write this down. I know there's a space for a formula on your paper. I'll tell you when to write on it. So this is the formula for coming up with a test statistic for correlation. And if we simplify it a little bit, it looks like this bottom one here, which still doesn't seem that simple, to tell you the truth, but we could go ahead and plug in our values for that. And when we plug in everything for our chirp data here, we get 16.21. Does that 16.21 look a little bit familiar? Have we seen a test statistic of 16.21? Yeah. If I back up here, look, this test statistic was also 16.21. And that's not a coincidence. It turns out mathematically that this funky, scary looking formula here for correlation at the end of the day turns out to be the same numerical value as just taking B1 over SE. And doesn't this seem like way easier to do than whatever this mess of a thing is over here? Yes, totally, right? So here's the 2-for part. So I'm going to give you multiple hypotheses that you can test with the same test statistic, which means you only have to learn how to do one test statistic to answer all kinds of different questions. So what kind of better deal is that? So basically here, if I want to do a test on correlation, then we can just use the same test statistic that we use to test the slope, and we can save ourselves all that extra work. So I call this my 3-for-1 special. So there's 3 different hypotheses that can all be tested with the same exact test statistic. So the first one is the slope that we talked about. So we can test slope equals 0 versus slope not equal to 0. The second one we just saw is correlation. So correlation equals 0 versus correlation not equal to 0. And the third one is we could also just test, hey, null hypothesis, no linear relationship between x and y, versus the alternative that there is a linear relationship between x and y. And all 3 of those hypotheses have the same test statistic. So look at that. I'm going to save you so much space on your cheat sheet because you're not going to have to write down 3 different formulas. Instead, you just have to write down 1 formula. And we already decided that this 1 formula was super easy to do because I'm going to give you a computer output that has B1 and SE on it, and then all you have to do is divide. So what could be better than that? And if I look at my hypotheses here, these are all 2-sided hypotheses, but I could do this 1-sided as well. So we could use greater than or less than for either of these. And on this bottom one here, if I wanted to say no positive, if there is a positive linear relationship or a negative linear relationship, that would make it a 1-sided test. So it's possible to do 1-sided or 2-sided tests with this. So how is this actually going to affect you when you're doing your problems? Well, you just have to be careful when you're reading the problem and see what it asks for. So if it's asking you to do a test on correlation, then write your hypotheses using correlation. Okay, if it's asking you to do a test on slope, then write your hypotheses using slope. If it's asking you to do a test to see if there's a relationship, then you can write your hypotheses this way. Also, just recognize that when it's asking about all these things, it all comes down to the same thing, because really all these things are related. They're all part of the same deal. So if your regression line has a positive slope, that would also mean that it has a positive correlation, and that would also mean that it had a positive linear relationship. So you can see that these are all intertwined concepts with each other. So that's why it makes sense that we could do them all with the same exact statistical test, getting the same exact p-value out of it. All right, so once we've come up with our model and we've talked about how we can use our model to make predictions, one question that we might have is, how good are these predictions? How good is our model at making predictions? And one way that we can measure how good our model is at making predictions is by looking at something called R-squared. Okay, and R-squared, to compute R-squared, we're basically going to take R, which remember is our correlation coefficient, and we're just going to square it. So R-squared is literally equal to R-squared. Now, once we do this, then what this R-squared measures is something different than what the correlation measures. So correlation measures strength of the linear relationship between x and y. But when we look at R-squared, what R-squared measures is the percent of the variation in the response that can be explained by the model. Okay, and I'm going to put or by the explanatory variable. I'll say the x variable, because our model only has one x variable. So it's the percent of the variation explained by that one x variable as well. All right, so what does this mean exactly? Well, let's think about when we're looking at height and weight. And let's say that we want to create a model to predict somebody's weight based on their height. So height would be x, weight would be y. Well, if I look at my sample data, then I would see that there's a lot of different weights in there. And one of the reasons why people weigh different amounts is because they are different heights, right? But is height the only thing that affects your weight? I mean, if I had 3 people that were all 65 inches tall, would they all weigh the same amount? No, right? What are some other things that affect your weight besides height? Gravity, that was funny. Okay, your eating habits, your body type, your muscle mass, how old you are, like how much activity that you get in a day. So there's lots of different things that can affect how much you weigh. Height is just one of many things that might explain why people weigh different amounts. So what this R squared is going to do is it's going to quantify that. It's going to say, okay, how much does height explain, and then how much is the variation because of all these other factors. Okay, so R squared is going to tell us how much of the variation in the response that can be explained by our X variable, and then the leftover is the stuff that's explained by everything else that's not in our model. So the higher your R squared, the better your model is going to be at predicting, because that means that that your X variable is able to explain a lot of that variation. So in the general public, looking at like a height weight model, it usually has a pretty low R squared, because all of those other factors, height plays a little part, but all those other factors play a huge part. So so really you probably wouldn't do a very good job making predictions solely based on somebody's height. But if you look at like athletes, like if I look at NBA players and I come up with a height weight model for my NBA players, then actually that model would have a pretty high R squared. So looking at somebody's height would actually give me a pretty good indication of how much they weigh. And that's because those NBA players have all those other factors are more similar, right? They're all active. They're all muscular. They're all all those things. They have a lot of things that are in common. So that model would be better. So because we're taking R and squaring it, R has values between -1 and +1. So that means that R squared is going to have values between 0 and 1. Or you could think of it as 0% to 100%. And in fact, frequently you're going to see R squared reported as a percent rather than a decimal number. So we talked about this already. The higher the R squared, the better the model is at making predictions. And something to keep in mind is that it is different from correlation. So it's not the same thing and it doesn't measure the same thing. And sometimes you're going to hear it referred to as the coefficient of determination. So I'm not going to call it that on the test, but somewhere in your Wiley Plus homework, or if you do any reading in the textbook, then you might hear a reference to coefficient of determination. And when they talk about that, they're just talking about R squared. It's just another name for R squared. But kind of to me, it sounds like a term that would come from like a Harry Potter book or something, like the Room of Requirement or something like that. Okay, so another thing about R squared that I just want to give you a heads up about is that computing R squared is pretty easy. If you're given R, all you have to do is square it and you get R squared. Ta-da! No problem, we can do that. A lot of times it's going to be given on computer output. So I know that on the exam, if I was to just be like, hey, here's R, what's R squared? Then you guys would be like, oh my gosh, she must think I'm so dumb. Like, how come she can't give me a more challenging question than that? And so I would not want it to make you feel bad like that ever. And so on an exam or something, instead of just saying like, here's R, what's R squared? Like I would probably use the definition of R squared to ask my question. So instead of just saying, hey, what's R squared? I would probably say something like, hey, what percent of the variation in temperature can be explained by chirp rate? And then you would be like, that's totally the definition for R squared. I can see that she's asking for R squared. She thought she was going to trick me, but she's totally not. And then you would just find R and square it, and then you would have your answer. So here's for the chirp rate data. R was 0.99062. So if I square that, then I get 0.9813. So that means that 98.13% of the variability in temperature can be explained by the cricket chirp rates. And that's a really high R squared. But we remember how we saw how close those points were to the line. So that's, you know, basically there's a very strong correlation there, which is going to make our model a lot better at making predictions and a lot of the variability being explained. Okay, so in the output, like here's just some examples of where you're going to see R squared. A lot of times it'll just tell it to you somewhere in the bottom somewhere. And you might see all different things in your Wiley Plus homework. The only one of these programs that I actually own is Minitab. So on the exam or something, it might look closer to this. All right, one last thing that we have to talk about, and then we're going to look at another big example here, and that is checking conditions. So anytime that we're going to use a theoretical distribution to come up with our p-values or come up with our confidence interval, margin of error, and stuff like that, then we have to make sure we meet the conditions for using that theoretical distribution. So that's what we have going on here. And for regression, the real conditions are actually a little bit more complex than we have time to talk about in our class. So we're just going to kind of have a quick check of the conditions based on two big ones that are going to be easier for us to check. So the two conditions that you need to know about are that one, the true relationship between X and Y is linear. And two, the variation of points around the line is constant. So those are the two main conditions that we're going to check. So let's think about how we would check these conditions, starting with the first one. So the first one, the true relationship between X and Y is linear. How could I look to see if the relationship between X and Y is linear? How do I figure out what the form of the relationship between X and Y is? It's basically the very first thing I always do, right? I graph it, I do my scatter plot. So when I initially do my scatter plot and I decide that it has a linear relationship, then secretly I'm also checking this first condition. So I can just do a scatter plot to check for that. So we're going to look at a scatter plot with the regression line on it. This second one here, the variation of the points around the line is constant. What that means is that we want to kind of have points bouncing up and down the same distance all along the line. So I'll show you another example in a minute, but here's just a basic one that I can draw out here. Okay, if this is my regression line and I just have points going on both sides of the line all over like that, then this is good, okay? When I'm talking about them being not constant, then that means that, hey, some points are really close to the line, and then as my X values get bigger, then they start getting like further and further away from the line. Okay, so you can see that the variation around the line is not constant in this second one. It's bad. So that's what we're looking for. And then another thing to be aware of that goes along with both of these is outliers. So the red flags that we're looking for on our graph that would indicate that we don't meet the conditions would be a curved or nonlinear pattern, consistently changing variability, or outliers and influential observations. So these are the kind of a more technical sounding way to look at the red flags. When we're talking about a curved or nonlinear pattern, this is where if we see rainbows or smiley faces or bananas, then those would all be B-A-N-A-N-A. Those would all be red flags. And then the consistently changing variability, I think that looks like a megaphone. So a megaphone shape would be bad, indicate that we didn't have constant variation. And then we have to check for outliers and influential points as well. So here's some examples. Okay, so if I'm checking for linearity, then this graph over here would be good. You can see it looks like the pattern of the points is definitely linear, pass the fat hot dog test. This one up here would be bad, okay, because that one has more of a banana shape. If I'm looking for constant variability, again, my graph over here on the left, that one's good because the points are bouncing around on both sides of the line about the same. And this one down here in the bottom right would be bad because on this one we can see that it has the megaphone shape. And then the third thing that we're watching out for is always those outliers and influential observations. So this one is that mammal longevity data. And the elephant here is an influential observation. And we can see that if I remove the elephant, then it changes the correlation quite a bit, okay, which would obviously have a huge impact on our confidence intervals, on our hypothesis tests, and all of that kind of stuff. So we always want to be careful for those, which is why we're always going to graph the data first. We're going to check all this stuff out. All right, so let's go ahead and look at another example, kind of start to finish here for our last 20 minutes of class. So this data came from a study that they did at Ohio State University, where they took some student volunteers and they randomly assigned them a number of cans of beer to drink. And then 30 minutes later, after drinking the beers, a police officer came along and measured their blood alcohol content in grams of alcohol per deciliter of blood. And this was the data that they have here. And they want to know, first of all, we want to know, is there evidence that the number of beers is useful for predicting blood alcohol content? And one thing, I don't have it on the screen here, but one thing that they talked about in the article that I got this data from is that all these students had, they were very different from each other. So we had males and females, we had, skinny people and larger people, and we had people with different drinking habits and all of that. So one thing that they thought was interesting about this study when they saw the results is that they thought that blood alcohol content would be a little bit more dependent on some of these outside factors. And here's the scatter plot here, and you can see that it has a pretty good relationship going on between number of beers and blood alcohol content. So it seems like some of those other things like gender, usual drinking habits and all of that don't have nearly as much effect as just how much did you drink. So we're looking for three things on our scatter plot: form, direction, and strength. So what would you say for form, direction, and strength? So yeah, I would call this linear, positive, and strong. So it definitely has a pretty tight fat hot dog going on here. Positive direction, so the more beers you drink, the higher your blood alcohol content will be. And it's pretty strong. They fall pretty close to that line. The correlation here was 0.894, which also would indicate a pretty strong linear relationship between these two variables. So here is our regression line. So we have predicted blood alcohol content is equal to negative 0.013 plus 0.018 times beers. And I feel like maybe some of you might have forgotten how to get these numbers in StatKey. And you should be able to do a scatter plot and be able to get the regression line from StatKey just like you did back in chapter 2. So I'm just going to show you real quick. So I took the data and I just typed it into Excel here, just straight from your PowerPoint. I typed it in here. So I've got one column for beers and one for blood alcohol content. So I'm going to copy this data here so that I can paste it into StatKey. So I'm going to come over here to StatKey. And in StatKey, I'm going to choose two quantitative variables, which is over here under descriptive statistics and graphs. So this should look vaguely familiar because we did this back in chapter 2. So I want to put in, I'm putting in my own data. I didn't have a prefab data set. So I'm going to click on edit data because I'm just copy pasting it. If they give you a data set, then obviously you can use that upload file to put your data in. So I've just pasted mine there and I'm going to click on OK. And you can see I get a lovely scatter plot, just like the one that I had in my PowerPoint. And there's a little toggle here where you can turn on and off the regression line. And then over here in this side box, it gives you all the information that you could ever want about this here. So it gives you the correlation, 0.894, and it gives you the slope and the intercept. So you could use this information to construct your line. All right, so thinking about the parameters, remember the parameters are the things that describe the population. So beta naught would be the intercept for the true regression line of beers and blood alcohol content if we measured everybody in the population. And beta 1 would be the slope for the true regression line, again, if we're measuring everybody in the population. So next I'm going to write my hypotheses. I'm going to do a test on the slope. I want to know if beers is useful for predicting blood alcohol content. And the way that I can test that is by doing a test on the slope here. So my null hypothesis is always the same when I'm doing a test on slope. So it's beta 1 equals 0. And then for my alternative, I chose to use greater than because even before I saw the data, it seems logical that the more beers you drink, the higher your blood alcohol content, right? I don't think anybody would really think, hey, if I have fewer beers, then I'm going to have a higher blood alcohol content. So it seems logical that it should be a positive relationship if there's going to be a relationship. So that's why I used greater than. So next we can check our conditions. So to do that, we look at our scatter plot with the line on it. And the two conditions are that the true relationship is linear and that we have a constant variance, okay? So looking here, I can see that I definitely have a linear relationship because I don't see any smileys, I don't see any rainbows, I don't see any bananas. As far as constant variance goes, I feel like I'm good with that because I don't see any megaphones. So there's no megaphones. And then I always also want to check to see if there's any worrisome outliers or influential observations. And looking here, it doesn't really seem like we have either of those. We have this person over here who looks like they drank 9 beers and they're kind of the only person out there. We only had one person that drank 8 also, but they don't really seem that far away or that far off the path. So I think it's all good. So we meet the conditions, which means we're ready to go on and we can compute the test statistic. So our test statistic is this magic 3-for-1 test statistic that we can use for everything. It's so great. And it's just B1 divided by SE. So here's some output here from some software. So I just need to find the B1 and the SE. So remember, I always want to get that stuff from my second line. And typically the name of that second line is going to be the name of your explanatory variable. So in this case, I'm going for these numbers right here. So the bottom coif number is my B1, and this bottom SE coif is my standard error. So I'm going to have 0.01796 divided by 0.00240. So if I do that calculation, 0.01796 divided by 0.0024 gives me 7.483. So my test statistic is 7.48. And you might notice that in these coefficient tables, it actually will typically give you the test statistic and the p-value for this test. But on the exam, like I have this crazy delete button on my keyboard, and like every once in a while, it just happens to delete things like test statistics and p-values if it thinks that you guys should be able to calculate those on your own. So it might mysteriously be missing on the exam. So just make sure that you know how to find that test statistic, which, as we mentioned, super easy and versatile because we can use it for everything. Just B divided by B1, I should say, divided by SE to get that value. All right, so then I'm going to want to find my p-value. So first thing I need to do is figure out my degrees of freedom. There were 16 students in this study, so degree of freedom is equal to n minus 2. So 16 minus 2 gives me 14 degrees of freedom. So in StatKey here, I am going to go to my T theoretical distribution. I'm going to tell it that I have 14 degrees of freedom, and then I need to put in my test statistic. So I'm clicking on right tail because I did a one-sided test. Remember, I had greater than in my alternative hypothesis. So I'm going to put in 7.48 down here on the bottom. And then this floating box here is my p-value. So 0.00000015, which is essentially 0. So that's my p-value. And remember, when we were looking at that output on this one, we could see that the p-value was rounded to 3 decimal places anyway, 0. So there we get it from StatKey. So now I'm ready to draw conclusions based on my hypothesis test. So that p-value is really, really, really low. And when p is low, then HO must go. So I'm going to reject the null hypothesis because we have lots of evidence that the slope for regression is positive. Or in other words, that number of beers is useful for predicting blood alcohol content. All right, so I've done this hypothesis test, but now I might want to know, okay, well, what is the slope then of this true regression line? And if I want to know what is the slope, then the appropriate statistical inference technique would be a confidence interval. So next we're going to do a confidence interval for the slope here. So recall that our confidence interval formula looks like this. So we have B1 plus and minus T star times the standard error. So here's kind of a list of all the things that we need to figure out before we can start plugging things into that. So the B1, again, all this information would come from the second line here of our table. You can ignore the first line. And the B1 is that first number. These are the same B1 and SE that we just used in our hypothesis test. So I get 0.01796 for my B1. Degrees of freedom was n minus 2. So in this case, that was 14. Our confidence level C, they tell us, is 95%. All right, T star, we'll come back to that in just a second. Let's write down our standard error first, which is, again, on the second line. I'm going to look at 0.0024. So to find my T star, all I need to know is degrees of freedom and confidence level. I'm going to go into the T theoretical distribution in StatKey, put in my 14 degrees of freedom and my 95% in confidence when I hit two tail, and that value is going to be my T star. So I put in 14 degrees of freedom. I click on two tail. I make sure 95 is in the center. That's what I wanted there. And so my T star value is going to be 2.145. So again, this is the same way we've been finding T star for all these other methods. So this should be a familiar procedure for you. So T star 2.145. All right, so now I basically have everything that I need, and I can go ahead and start plugging these numbers in. So I'm going to take the B1, which is 0.01796, plus and minus my T star, which is 2.145, times the standard error, which was 0.0024. Multiplying out the right-hand side, the 2.145 times the 0.0024 gives me 0.005148. That's my margin of error. So I'm going to add and subtract that from my slope estimate. And so if I take 0.01796 minus 0.005148, I get 0.0128 for my lower bound. And then 0.01796 plus 0.005148 gives me 0.0231 for my upper bound. So this is my confidence interval. And there's kind of two ways to write the conclusion for your confidence interval. You can stick with kind of our standard format that would say we're 95% confident that the slope for the regression line of beers and blood alcohol content is between 0.0128 and 0.0231. And if you write it like that, it's just fine. I kind of call that the conclusion 1.0, but if you want to take it to conclusion 2.0, then you can incorporate the definition for slope, or the interpretation of slope, I should say, in your conclusion. And if you do that, it would look more like this. So you'd say we're 95% confident that for every one beer, blood alcohol content increases between 0.0128 and 0.0231 on average. So I like this method because I feel like it's a little bit more interpretive. But if the other method makes sense to you, it's still valid, still a good one. All right, so now we've done a hypothesis test, we've done a confidence interval. One more question that we might get asked about this data is, what percent of the variation in blood alcohol content can be explained by number of beers? And if I ask a question like that, what am I really asking for? Like, what's the quantity that I'm telling you to find? Or what's the symbol for the quantity? Let's start with that. So when we're talking about the percent of the variation in the response that can be explained by the X variable, we're talking about R squared, exactly. So R squared in this case is right here in the output. They just gave it to us, 79.98%. So that would be the answer. So 79.98% of the variation in blood alcohol concentration, and that should say content, I guess, because that's what I defined it as earlier, can be explained by number of beers consumed. Now looking over at my output here, notice that there's some variations on R squared. We have R squared ADJ, which stands for adjusted, and R squared PRED, which stands for predicted. Don't use any of those, okay? Just stick with the plain old simple old regular R squared. So if there's ever any extra things there, don't use that one. Just use the regular R squared value. Okay, one more thing that I want to point out about this R squared is that calculating R squared is just taking R, the correlation, and squaring it, right? We can also go in reverse. So if you're given R squared, you could figure out what the correlation is. So R would just be the square root of R squared. So some key things to keep in mind here when you're doing it this way, though, because it can be a little bit trickier going this direction. First of all, a lot of times R squared is given as a percent, but when we do calculations, we should always turn everything to a decimal. So in this case, if I was trying to figure out R, I would want to change this to 0.7998 before I took the square root. So taking the square root of that, square root of 0.7998 gives me 0.894, which was what the correlation was, if you remember from when we looked at it in the beginning. The other thing you need to remember, though, whenever you square root something, the answer could be either positive or negative. So you have to look back at your data and decide whether this should be a positive R or a negative R. And you can figure that out by either looking at the slope, because the slope and R should have the same sign. You could look at the scatter plot, because then you should be able to tell if it's a positive or negative relationship. But keep in mind, especially if you keep getting things wrong over and over on Wiley Plus, and you're like, hey, I know I'm doing this right, then realize that this could be positive or negative. So if you look back, maybe you should have had a negative correlation after you square rooted. So if you remember those two things, then going this direction is a breeze.